Most of the transmission line problems involve the use of complicated equations. The solution of such problems is tedious and difficult because the accurate manipulation of equations is necessary. To simplify their solutions, we need a graphic method of arriving at a quick answer. The popular chart is developed by Philip H. Smith known as Smith chart. The chart consists of a plot of the normalized impedance or admittance with angle and magnitude of a generalized complex reflection coefficient in unity circle. That graphic aid, somewhat modified over time, is still in constant use in microwave electronics and other fields where complex impedances and transmission line problems are found. The Smith chart is indeed a powerful tool for the RF designer. The modern Smith chart is shown in figure and consists of a series of overlapping or orthogonal circles, that is, circles that intersect each other at right angles. The set of orthogonal circles makes up the basic structure of the Smith chart. A baseline or center horizontal axis is highlighted in this figure and it bisects the Smith chart outer circle. This line or horizontal axis is called the pure resistance line and it forms the reference for measurements made on the chart. A complex impedance contains both resistance and reactance and is expressed in the mathematical form Z is equal to R plus or minus J X ohm. Z the complex impedance, R the resistive component of the impedance, X the reactive component of the impedance. The pure resistance line represents the situation where X is equal to 0 and the impedance is therefore equal to the resistive component only. In order to make the Smith chart universal, the impedances along the pure resistance line are normalized with reference to system impedance. For most microwave RF systems, the system impedance is standardized at 50 ohm. To normalize the actual impedance, divide it by the system impedance. For example, load impedance is given in ohm. The normalized impedance is calculated by dividing the given complex impedance by system impedance, which is in the form R plus or minus J X. Normalized impedance is dimensionless. The pure resistance line is structured such that the system standard impedance is in the center of the chart and has normalized value of 1.0. This is the center of the chart, denoted as O. This value derives from Z0 divided by Z0, which is equal to 1.0. To the left of the 1.0 point are decimal fraction values used to denote impedances less than the system impedance. Similarly, points to the right of the 1.0 are greater than 1 and denote impedances that are higher than the system impedance. By using normalized impedances, we can use the Smith chart for almost any practical combination of system and load and source impedances, whether resistive, reactive, or complex. The conversion of the normalized impedance to actual impedance values is done by multiplying the normalized impedance by the system impedance. That is, for example, Z is equal to normalized impedance into system impedance, which is equal to R plus JX. Resistance circles. Normalized resistances are shown as resistance circles. The normalized resistance of any point is found by following the resistance circle to the horizontal axis and reading of the value. This point is always center of the Smith chart, where VSWR is equal to 1. At this point, VSWR is equal to infinite. At this point, VSWR is equal to 0. On the horizontal axis, we read the resistance circle values. Reactance circles. Reactance axis lies along the circumference of the Smith chart. Values are labeled on the axis. Normalized reactance is shown as reactance curves. The circles above the pure resistance line represent the inductive reactance. The circles below the pure resistance line represent the capacitive reactance. Outer circle parameters. Circle A is the reactance circle. The circle B defines the wavelength distance relative to either the load or generator end of the transmission line. There are two scales on the wavelength circle B, and both have their zero origin on the left hand extreme of the pure resistance line. Both scales represent 1/2 wavelength for one entire revolution and are calibrated from 0 through 0.50 such that these 2 points are identical with each other on the circle. In other words, starting at the 0 point and traveling 360 degrees around the circle brings 1 back to 0, which represents 1/2 wavelength or 0.5 lambda. Although both wavelength scales are of the same magnitude 0 to 0.50, they are opposite in direction. The outer scale is calibrated clockwise and it represents wavelengths toward the generator. The inner scale is calibrated counterclockwise and it represents wavelengths toward the load. These two scales are complementary at all points. Circle C defines the reflection coefficient angle in degrees. The scale starts at 0 degree on the right hand end of the pure resistance line, which corresponds to an infinite resistance, and it goes halfway around the circle to 180 degree at the 0 end of the pure resistance line. The upper half circle is calibrated 0 to plus 180 degree and the bottom half circle is calibrated 0 to minus 180 degree. Reflecting inductive or capacitive reactance situations respectively. Radially scaled parameters. We can determine VSWR using D line. We can determine return loss in decibels on E line. We can determine magnitude of reflection coefficient on F line. And using G line, we can determine transmission coefficient of the transmission line. Characteristics of Smith chart. There are two families of orthogonal circles in the chart, constant R circles and constant X circles. The upper half of the diagram represents plus Jx and lower half of the diagram represents minus Jx. For admittance, the constant R circles become constant G circles and the constant X circles become constant susceptance B circles. On the chart, impedance representing by R plus Jx form and Y is G plus JB form. The distance around the Smith chart once is 1/2 wavelength, that is 0.5 lambda. The horizontal radius to the right of the chart, center to the horizontal radius to the right of the chart center corresponds to Vmax, I minimum, Zmax and standing wave ratio. The horizontal axis To the left of the chart center corresponds to V minimum, I max, Z minimum and 1 by standing wave ratio. Consider an example in which system impedance is 50 ohm and the load impedance is 95 plus J55 ohm. Here we will see how to mark the impedance on the Smith chart and how to find out the admittance for that corresponding impedance on the chart. Initially, we have to find out normalized impedance. Normalized impedance is given by given load impedance divided by system impedance, which is equal to 95 plus J 55 ohm divided by 50 ohm, which is equal to 1.9 plus J 1.1 is normalized impedance. Normalized ZL is 1.9 plus J 1.1, which is in the form R plus JX. So in the Smith chart, 1.0 is always center of the Smith chart, name it as O. So here I have to mark R equal to 1.9 resistance circle. This is 1.2, 1.4, 1.6, 1.8 and it's 2. Therefore, my R is equal to 1.9 circle is between the 1.8 and 2. So I can say this is 1.9. So and plus J, that's why I have to move along this circle upward. And now I have to mark the J 1.1. So reactance circle, this is 1.0 and it's 1.2, therefore this is 1.1. So 1.1 reactance circle should coincide with 1.9 R circle. This is a coincide point. Name it as A, and this is normalized ZL 1.9 plus J 1.1. Now draw OA radius. With OA radius, draw the VSWR circle. So now we have marked the ZL on the Smith chart and drawn VSWR circle. Now we have to find out the admittance corresponding to the ZL impedance on the same chart. For that, impedance radius OA extended to the B through the 1.0 center point until it intersects the VSWR circle again. AB line intersects at point B is the admittance point on the Smith chart. It is equal to, so this R circle coincides at the B point and this X circle coincides at B point. So this is point 3, it's point 4, therefore R circle is 0.39 minus J 0.2, 0.3 and it's 0.22 and it's 0.44, and in between 0.22 and 0.24 x circle is 2.23. So normalized admittance is equal to 0.39 minus J 0.23. Therefore, admittance is equal to normalized admittance multiplied with the Y naught. Y naught is equal to 1 by Z naught. Therefore, Y is equal to load admittance for the given problem 0.39 minus J 0.23 divided by 50. Therefore, YL is equal to 0.0078 minus J 0.0046 ohm. This is the answer for the example problem.